Might as well start. So welcome to the condensed matter seminar. I'm very pleased that we have Wang with us today, because Yong is a bit of a computer expert. He has done some monstrous simulations on the melting problem by sort of, actually the melting problem you may think that's well understood. Actually, it's not. And the melting of systems, no matter whether you talk about two-dimensional systems or three-dimensional systems, is still a bit mysterious, to say the least, for various reasons. And although it's an ancient problem, it's probably still something which is not properly understood. And so today we're going to hear from Yong about some recent work he has been doing, actually with a number of collaborators, including me. Well, I wouldn't say including me. I basically all I do is write a bit of the paper. But the most of the results we obtained are in a PNAS article, a fairly recent PNAS article, what was it, May or something like that. And his title is Towards a Deeper Understanding of Melting Through AI-Driven Molecular Simulations. And so, be interested to hear what he has to say.
Okay, thanks, Mike. Hi, everyone. I'm Wang. I'm currently a postdoc at Princeton. So I really appreciate your invitation and support on this talk. It's my great pleasure to be here today and to share some of my research. And my research about melting since I was a junior graduate student. So before I start, I'd like to acknowledge that I'm still trying to find a comprehensive outline for this melting story. And my simulation could be limited by a lot of factors. So please feel free to raise your questions and your comments at any time. Let me first give some context. Melting is an ubiquitous phase transition in our daily life. Theories to understand it started from Lindemann criterion, which proposed that melting occurs when atoms in a solid vibrate beyond a certain displacement. And later, theories based on the coexistence of two phases across the transition, such as the classical nucleation phase transition theories, were developed. And in this framework, melting is understood as a competition in free energy between solid and liquid phases. And then we come to molecular simulations, which allows us to study real materials under controlled conditions and directly observe melting at the atomistic level. So this cell shows the coexistence of liquid and solid water, locating the simulation temperature to melting point. So this kind of numerical simulations provide a platform to validate and refine our current melting theory. Despite these advances, as Mike said, a unified theoretical framework that can fully describe and predict melting across different materials and conditions is still lacking. Let me show some examples beyond traditional melting theories. So first, there is premelting. Here, a thin quasi-liquid layer could form at surface or interfaces, such as gray boundaries, well below the bulk melting temperature. And most of our melting theories only focus on homogeneous bulk behaviors and overlook these surface effects. So second, the superionic state. In this state, light atoms within a compound melt and diffuse first, while the heavier sublattice remain solid. A well-known case is lithium conduction in batteries. here I show another example is high pressure ammonia. Inside this compound, hydrogen ions become diffusive while nitrogen sublattice remains fixed. And this superionic state can persist over a wide temperature and pressure range in the interior of giant gas planets such as Uranus and Neptune, making it a crucial behavior for understanding their thermal and electrical transport property. So what we usually discuss is 3D melting, but in low dimensions, such as 2D, things are very different. In fact, 2D melting can be described by the KT-HNY theory, which comes from the Causley-Stoller's theory of topological phase transitions. The key idea is that instead of melting directly from solid to liquid, a 2D solid passes through an intermediate state called hexagonal phase. And these phases can be confirmed by both looking at the topological defects and the how translational and orientational order decay. And according to the original KT-HNY theory, both the solid to hexatic and hexatic to liquid transitions are all continuous. Okay, so why is developing a general melting theory so challenging? In my opinion, there are several reasons. For example, melting is actually a multi-scale problem. To understand it, we must capture and harmonize its transition details at different scales. And it can happen at different conditions. And it's also highly related to specific material properties. Like, for example, for systems with unharmonicity and nuclear quantum effects, we cannot simply understand its melting using harmonic vibrations. And some emergent behaviors, such as the large fluctuation and many-body correlations, may play a big role, making it more than just a sum of local events. And also, how to unify dimensional difference in melting is a problem. And the main tool I used is molecular dynamics. It's a numerical experiment based on Newton's equation that allow us to observe atomic motion directly. And the important part is the reliability of MD simulations actually depends on the interatomic potential we choose. There are two typical MD methods. The classic MD can handle very large systems up to millions of atoms at a long time scale to nanosecond. But the trade-off is the lower accuracy. It relies on some empirical models. And by contrast, ab initio MD, AIMD, can calculate forces and energies directly from the method based on quantum mechanics, like the density function theories, DFT. And this gives us a much higher accuracy. But because of its expensive computational cost, it's only for small systems, like hundreds of atoms and short timescales to like typical picoseconds. So we want AIMD level accuracy and classical MD efficiency. Recent advancement in machine learning allow us to do this. By training a machine learning potential, we can perform large simulation with quantum mechanical accuracy. So the overall workflow is very simple. So first, we collect reference data, calculate by some electronic method like DFT using small systems, and then we represent each atom's environment with different descriptors, and finally use regression like neural networks or the kernel method to learn the potential energy surface and to perform the MD at a large scale. So another advantage for the machine learning potential is its flexibility. So by changing the training set, the same model can handle complex materials and diverse thermodynamics. And that's why I use it in my research, because there are a lot of systems cannot simply described by empirical models. So with these backgrounds, Let me first turn to the first part of my melting work, atomic collective motion in high pressure temperature metals. We choose calcium as our case. Under pressure, calcium shows an unusual structural sequencing from FCC to BCC, then to simple cubic. This is somewhat counterintuitive because we expect as pressure goes up, the pattern would be denser. Prior studies suggest that this anomaly is linked to calcium's unique high pressure properties. In particularly, the simple cubic phases display strong unharmonicity and complex phase computation at low temperatures. Motivated by this, we focused on its melting behavior in the simple cubic phases. By training a machine learning potential, we identified a low diffusion state between solid and liquid at high temperature. Vibrational spectra also show the intermediate signals consistent with the diffusion state. By looking into the MD trajectories, we found that this kind of diffusion originates from a pre-melting process with collective atomic motion along the SC lattice axis, specifically its 100 direction. And the transition barrier calculations confirm this diffusive priority, which is linked to high pressure unharmonicity and the strong phonon softening of corresponding mode. And from the electronic side, we found that in simple cubic calciums, electrons are highly localized, and it can form about 0.61 charge sitting at the body center of the simple cubic lattice, acting like a quasi-ion. And this reduces the density of state at the Fermi level, making SC calcium only weakly metallic. And during this pre-melting collective atomic diffusion, the pseudo gap remains, but it disappears in the liquid, suggesting that the 1D diffusion is stabilized by this electronic feature. And our entropy and free energy calculations further confirm that this 1D pre-melting is a stable intermediate state. Finally, the phase diagram revealed there is the pre-melting region inserted between solid and liquid, which can naturally explain the sharp change observed in calcium experimental melting curve. So next, I wanted to share how this type of collective pre-melting, atomic collective pre-melting can affect the material's properties and maybe our daily life. So the story is about the Earth's inner core, which is solidified from liquid and is mostly made by high pressure and near melting iron. We know the Earth's layer structure mostly by seismic waves, consisting of longitudinal P wave and the transverse S wave. For S wave, there's a clear reduction of its speed in inner core, because we see in the metal, S wave is about half of P wave, but in the inner core it's only 1/3, and this is called the shear softening of the inner core. And in 2013, this paper performed AIMD to study the melting of behavior of high pressure, high PT ion. And they found there is a sharp reduction in elastic constants, especially shear modulus, near melting and the softening of shear modulus could induce the softening of S wave. Unfortunately, due to the small size they used, the inherent reason why there is a softening could not be explained. 2 years ago, some researchers tried to add light elements, such as hydrogen, into the inner core ion and use the diffusion of these light elements to address the softening. However, as seen in this paper, the pure ion could also behave the softening. Working with high-pressure experimentalists, we studied iron near its melting point, and the experiments directly observed S-wave softening in pre-melting HCP ion. We trained the machine learning potential that accurately captures ion-ion interactions, and our calculated elastic constants and wave velocities agree well with the experiment. And more importantly, our simulation revealed collective atomic behavior also existing in premelting ion, and this behavior is linked to strong phonon softening along certain direction near melting. In the Earth's inner core, the presence of defects and light elements could further enhance such diffusion, leading to a strong attenuation of shear wave and a reduced wave speed. The system we simulated above are non-structures, but sometimes we want to predict the crystal structure given all in the conditions and elements, and then study their finite temperature dynamics. This brings us to the problem of crystal structure prediction in CSP. In CSP, candidate structures are generated, involved, and relaxed to find a minimum energy structure with quantum method. We recently replaced some of steps with machine learning, greatly improving efficiency while retaining the DFT accuracy. So if we view it from energy landscape perspective, the role of CFT method is to efficiently guide exploration of possible stable crystal across a rugged energy landscape. Combining CSP and machine learning MD, we can extend our scope to dynamic properties of new materials. Two examples I want to present using this combination. The first one is about novel superionic materials. In 2017, researchers predict the stable high-pressure helium-sodium compounds using CSP and successfully verify it experimentally. And this opened the door to study the high-pressure helium compounds. In 2019, we predict the stable helium water crystal under the conditions of Neptune and Uranus using CSP, and upon heating, this compound would have two superionic phase transitions, in which the helium melts first, and then hydrogen start diffusing at higher temperature, while oxygen sublattice remains solid before fully melt. Another example is about 2D melting in confined layer solid, which I worked with Mike. We have talked about 2D melting before, and to study it, most of the experiments using confinement technique to trap systems in 2D. Early studies often use colloidal particles between two plates, since they are easier to control the atoms. These experiments revealed a structural pattern, for example, from one monolayer hexagonal structure to two-layer tetragonal layer, and then to two hexagonal layers, and so on. According to the KTH1 theory, 2D melting should be two-phase transition should be continuous. However, some 2D confined systems on monolayer have shown that there might be a discontinuous melting, and further studies suggest that the 2D melting scenarios depends on many factors, such as interaction type we use, confinement geometry, and the finite size effects. For real atomic systems, confinement studies took off around 2010 because of the emergence of 2D materials like graphene. A key example is square ice confirmed between graphene layers experimentally, but Matthias told me this paper has some problem, but but it's still worthwhile to talking about this. And later, crystal structure prediction techniques confirmed this finding. And in these systems, the phase diagram is mainly controlled by two parameters: the confinement width between graphene layers and the lateral pressure we applied in XY plane. More recently, using finite temperature machine learning molecular dynamics, research proposed that there should be a 2D hexatic water confined between graphene. So far, few studies have looked at the 2D confinement of simple elements like noble gases and alumina. In 3D, these materials are very rigid. For example, helium stasis HCP, which is hexagonal close packing pattern, up to 30 terapascal. This is actually the pressure of white dwarf stars. But when they confine between graphene layers, our CSP found they can form this kind of square patterns similar to confined colloidal particles and ice. And by tuning the confinement width and the lateral pressure, we mapped out full phase diagrams. The system evolved in the sequence from one layer close packed to two layer square and to two layers hexagon and so on. And we found as the confinement width enlarged, this type of square pattern fade away and eventually disappearing at around 5 to 7 layers, leaving all in the closed packed arrangement we are familiar with. With these predicted stable structures, we can simulate their finite temperature behaviors. For monolayer neon, we found its melting perfectly aligned with the KTH1 theory, with two phase transitions are continuous. Okay, so if we look at the defects evolution in monolayers, we see that the dislocation emerges and the system enter into hexatic phase. And after melting, the number of dislocation decrease and the number of disclination increase because of the unbinding of dislocations. For multi-layer systems, we first see a continuous transition from solid to layered hexatic. And this is not only confirmed by the KTHY signal, but also the z-axis density profile. In solid, layers remain isolated. And in liquid, interstitial atoms surge to the same level across different layers. But in the layered hexatic, only a few atoms are exchanged between layers. As melting proceeds, the formation of 3D defects in liquid reduces the 3D defects in the liquid reduces the number of 2D defects, both disclination and dislocation, linking the two defects populations. So finally, to probe the order of this melting, we performed a large-scale hysteresis simulation with about 1 million atoms over 100 nanoseconds. And this clearly shows that the melting in multi-layers case is discontinuous. Okay. Lastly, I want to share some recent progress in machine learning for molecular simulations. This timeline shows how computation in science has evolved over the past centuries. Actually, my previous work mostly fell into this range. In these works, I trained a machine learning model for specific systems and tailored it to the problem I'm interested in. And now the field is moving forward to universal foundation models trained on massive, diverse dataset and fine-tune a particular system with minimal extra effort. Here is an example called Maze-Off. They develop a large model that can basically well describe for a lot of different molecular systems. We also contribute to this direction using the GPU-MD software we developed, and we trained the model mostly for metals and alloys. Compared to the traditional embedded atom method used for decades, our machine learning model delivers far higher accuracy and efficiency. This means we now can simulate microscopic atomic behavior with quantum mechanic accuracy. So that's the melting story I want to share today. And I want to appreciate all the people who support and guided me along the way. Without them, I could not explore and develop freely. Thank you for listening. I'm happy to take any questions you may have. Thanks.
Now, I'm sure there are some questions on
Sure.
this topic.
I had a question. So on the collective premelting story, maybe could you explain? I'm not sure if I missed it. Why collective premelting happens? Is that just a result? Like physically, why does it happen? Is it just a result of the simulation, or is there some way we can understand?
It's because a lot of factors, but give me a second. So the first one is there is an abnormal softening in certain phonon mode at high temperature, and there is an ambient case. This is a BCC titanium, and its phonon spectra was observed that there is a strange softening here, and this can be explained by this type of collective behavior. So because there is a softening along certain direction, this means that some mode can be easily triggered to form this kind of atomic collective motion.
So should I think of this collective motion as being the motion of maybe some subset of local defects, or is it some I don't know, long wavelength mode that's soft?
Yeah, you can't see it in this way, but we are talking about the perfect bulk without defect. If you say it's defect, it spontaneously occurred from a perfect crystal.
I see.
In all your simulations, they're done at constant volume?
What?
Are they done at constant volume?
Volume. Some of it down constant pressure.
So some are done in.
Yeah, some of them.
Because it seems to me that when investigating phase transitions, it'd be better to use constant pressure.
Yeah, exactly.
Because then this issue with trying to distinguish between two-phase coexistence and some kind of
especially when you to calculate the melting point using the coexistence of solid and liquid, you have to use a constant pressure.
Right.
Yeah.
Okay.
Oh, you can go.
Okay. For like the collective pre-melting, does it happen for like both 2D and 3D cases, and like does it make a difference by like
this
for
actually
different
a good
materials?
question. So for 2D melting, the typical defects is disclination and dislocation. So I'm not sure whether there is a collective motion in particles. So I'm not sure.
In what particles?
Like the system we studied, the monolayer neon, we didn't find this kind of collective motion.
I see. Were you able to find a pattern in like what kind of materials would have this property?
Oh yeah, that would be. So from my perspective, the phonon symphony is the most straightforward signal along certain some weird softening in its phonon spectra.
I'm sorry, what is that?
Okay, so for the crystal, we can calculate its phonon spectra. So this means that their vibrational mode and the corresponding frequency, and for the system with collective behavior, the sum of mode, sum of direction would be much would be much softer, would become much softening compared to the other mode. You can see this is the 600 Kelvin. The blue line is 600 Kelvin, and the red line is 200 Kelvin. And so for this mode, it's strongly reduced at high temperature, and this corresponds to the vibrational mode along the 100 axis.
I see.
Yeah.
Thank you.
Sorry, I wanted to. So since we're on this collective premelting, I'm trying to understand. If I look at your simulation, it looks like you have these localized 1D, maybe defects or something moving along. But if in a phonon picture you're in some momentum space, which that would be some wave that is macroscopic over your whole system. So I'm just trying to connect this localized picture that you have with the fact that you have some soft mode. Like why is the melting kind of like localized to atomic scale
Yeah.
movements? Yeah.
So here the system I show is just a small part of the system. So if we enlarge the system, this type of diffusion can across a large scale in the system. So you can consider it's like it's a wave.
Yeah.
Yeah, it's like a wave.
I see. So
Not like a defect.
I see.
I was wondering in the PNAS work, like you showed these different noble gases between graphene layers. What's the role of graphene, and does it matter that it is graphene?
Yeah, in graphene need to confine the atoms to squeeze it along to apply pressure along the z-axis.
Right, but like the fact that it is graphene doesn't matter. You could do a layer of hexagonal boron nitride, for example.
Yeah.
Okay.
Yeah. This is a general
It's just
situation.
Okay, I
Yeah.
see.
Got a question. I mean, you're confining potentials, not really potential
Graphene, yes.
due to graphene. It's just the potential.
Uniform
Flat
graph
plate.
along, yes.
Yeah.
Yes,
Okay.
yes.
Have you had any insight into this peculiar sequence of structures you have in the crystals with width? Where you've got to start with a sort of one layer triangular crystal, goes to
Square
two
face.
layer square, and
Yeah.
which goes to two layer triangular, and so on and so forth. Have you got any insight as to why that happens?
There is actually a simple theory to describe it called free volume theory, which means so if we because the confinement apply the pressure along the axis to the system, and the confinement width is fixed, so the particle need to find the most the largest free volume with its neighbors, and if it goes from one hexagonal to two hexagonal, the intermediate range, the free volume of this type of two-layer hexagonal is smaller than this type of two-layer square face. So this is why the square face can exist.
Oh, okay, so when you say square and triangle, you're talking about layer by layer.
Yeah, you're right.
Okay. Now,
Thank you.
in a typical simulation, how many particles are you actually using? In the millions.
Yeah. Now we can do millions. Yeah, like this general purpose machine learning potential, we can simulate 100 million atoms to nanoscale in 1 week using 8 GPU and retaining the quantum mechanics accuracy.
pretty good.
That sounds pretty spectacular.
Yeah. Yep. Oh, beyond what
Just like on that question, so how long does it take to actually generate the like actually train the machine learning model? So this is the 1 week is after you've spent all the pre-processing to develop.
No. The simulation takes 1 week.
Right.
But the training of that,
part.
training of model is a tricky. It takes like, for general purpose, it takes maybe 1 to 2 months. But if there are a lot of materials, repositories online, so you can download their structures and the energy and forces, so you can. This will save a lot of time.
I see.
Yeah.
It's just all front. Essentially, the cost is all front loaded by somebody else.
Yeah.
No, no more questions. Perhaps you could thank Yong for a very informative talk.